Hey everyone, I'm Rami. This is Rami plus fans, so that must make you the fan. And so, as you can see today, we have broken out something new. No more paint, no more using my mouse to draw stuff. We have finally gotten a tablet. I even got in a tablet glove. Don't know why, but hey, it looks cool. And we have a pen. And so, today, we're going to start lecturing first and foremost just to see how it looks on YouTube, how it feels writing out an actual lecture, and going from there. Today's lecture is not really planned. It's going to vaguely start with vector products like the cross product, the dot product, maybe some curl, maybe some divergence, and rewriting it in different languages and paradigms to show you that you don't need to stick by the cross product. You can use stuff, new products such as the wedge product, comboed with something called the hodge star, and you can get the same formulas, the same formulation, the same computations, um, but in a different way, and it's kind of fun. So I think what I'm gonna do is this is probably gonna be like the start of that series and like how you can like reformulate, even stuff like, Hamiltonian mechanics with, simplex forms and how differential forms and exterior calculus fit in there, uh, how it works in general relativity, how it works in thermodynamics, how it works in electromagnetism, and even I'll think about it. I would have to think about how I can incorporate it in, um, quantum mechanics and quantum field theory. So, without further ado, let's start with this idea that I'm given two vectors and I need to multiply them. The one way you guys know about them is to cross product and the dot product usually. So I look at these three vectors and I say, cool. Well, if I were to cross this, the first time I saw this product, I would immediately go to something known as the 3 by 3 determinant. And maybe you're like me and you're a physicist, and when you're a little baby physicist, you'd write IJK up here, right? Miss them, but we're not doing physics today. We're doing math. So I'm going to write this as my unit vectors are going to be x, y, and z. And my components are going to be 1, 1, 1 for the A, and x, y, z for the B. And so if you remember how to do this is you take one unit vector, we'll take the x, we eliminate what's underneath of it, we eliminate what's to the side of it, and then we're left over, oops, I forgot to put an equal sign. We're left over with four things, and we're going to do a 2 by 2 determinant. And if you remember, a 2 by 2 determinant is defined to be this multiplied by this, so AD minus BC. I wrote the wrong one. So in this case, it's going to be 1 times Z, which is Z, minus 1 times Y, which is Y. And you're going to do this for all of your unit vectors. So it's not just going to be this one. You're going to have to do it again for the Y. And once again, dogmatically, I'm going to have to tell you there's a subtraction sign there. Why? I wouldn't be able to tell you off the top of my head. Right? I just know you have to write a minus sign here when you're using this formula, and it could come from some more, you know, underlying reason. I can explain it in exterior algebra, which we'll see. But when using this formulation, I wouldn't be able to tell you. So you have to write a subtraction sign here, and we're going to do it for the y now. And so once again, you eliminate what's underneath for the y and what's up to the side of the y. So what's left over is 1, 1, x, and z. And we do our 2 by 2 determinant. In this case, it's going to be 1 times z, z, 1 times x, x, y hat. And then once again, dogmatically, it's an addition sign now. Why are we adding? Hey, that's just how it goes in this way. Um, And so let's do it finally for that one. So we're going to get the 2 by 2 determinant, 1, 1, x, y. And so that gives us y minus x, z hat direction. And so you just computed the cross product, right? The cross product is a vector product that returns a vector, right? So you see we're left over with a vector. We have components and we have direction, right? So we have a vector. And so the answer to this problem using this computation formula, I prefer writing it this way. And so I'm going to distribute the negative sign because I really don't like negative signs. So I forgot I can scroll down. I really don't like negative signs, right? So I'm going to distribute that negative. And so we get z minus y. Distribute that. We get x minus z. And then we get y minus z. And so we just computed our first cross product. Um, and so the interesting thing about this is it's kind of like dogma, right? You doing a 3 by 3 determinant. Uh, why am I writing the stuff up there? Why is there a minus sign? But it gets the job done, right? And so the other one you may be aware of is the vector dot product, or in this case, a scalar product. And the answer is going to give you a number. And in this case, when you dot two vectors, which I'll write like this, you literally just multiply their components together. So in this case, I literally just multiply these together. So what do I get? I get x, y, and z. And the reason for this is because of this condition. This condition that we're working in an orthogonal coordinate system. And what that means is I assumed I was working in that XYZ space that we all know and love, right? And so what this means is that if I multiply two unit vectors together, if they are in the same direction or they are parallel to each other, we're going to get a 1. But if they are not, if they are 90 degrees to each other, we get a 0. So that's why I don't really consider the multiplication this way, because this is going to be x hat times y hat. And so vectors are going to be multiplied with each other here. And what is x hat times y hat? Well, that's just 0. So it goes to 0. So that's the way I think about it, right? And so there are more formulas for these things as we get more and more abstract. So like that's the way I think about these things initially off the top of my head. This vector stuff right here may not be, the most formal way of looking at it because it's just the first way of looking at it. That's how I look at dot product right off the top of my head, and that's where how I look at a cross product right off the top of my head. Um, and so if we want to up the abstraction, we want to up the way we want to look at this, there is another way of looking at vector cross product and the vector dot product. One way is introducing symbols. So I'm going to write two symbols for you guys, and there might seem kind of weird right off the top of the head. So one of them is what's called the Kronecker delta. It can look like this, but in this case, because we are in what's known as flat Euclidean space, I can lower them both. And this product or the symbol has the property, one second, that if I equals j, it's 1. Oops, I put a 0. And you'll see why I put a 0 right at the top. It's the next one. And it's 0 if I doesn't equal j. And what that means is if I ever write this, for example, 1, 1, this means I will replace wherever I see this symbol with a 1. But if I ever write delta 1, 2, I will get a 0 because that's what the symbol does. And so where I'm going to introduce this for you is going to be in the vector scalar product. Because remember, what did I say above? If I have x hat, y hat, that gives me 0. But if I have the same thing, that gives me 1. Wait a second. If I have the same thing, it gives me a 1. If I have a different thing, it gives me a 0. That's exactly the behavior we have here. So, we can now rewrite this product in a more abstract way. I can now write A, which I'm going to rewrite A here real fast. I'm going to rewrite A in something that's called Einstein's summation convention. And so I'm going to rewrite A as this, where because I want to add this over, because remember, what is A actually? What is A actually? A, if you remember, was 1, 1, 1. Written out, it's going to be x hat plus y hat plus z hat. So, using this notation above, you see that I need to get 3 components. I need to have 3 things here. And so what this means is I'm going to sum, because I'm adding here, I'm going to sum over these indices. And how many do I have? Well, I have 3 because I have 3 dimensions. So in this case, this is going to be equal to A1, E1 plus A2, E2 plus A3, E3. And I have to write off to the side there because that's getting in the way. So I'm going to erase this. So that is going to be the new way we're going to be writing vectors. Vectors are equal to this. Okay? That's the way you want to be thinking about them. It's the same thing. It's how many components I have. I'm going to write out, I'm going to sum over them. I'm going to literally add them over and over and over. So, for example, to give you another little taste of it, B was equal to BI EI. And now I'll pause here. Does it matter if I write this as, oops, no, right? All we really care about is, are they the same letter? Are they the same thing? If they are the same thing, we sum over them. If they are not the same thing, we don't sum over them. So in this case, it doesn't really matter. But for clarity's sake, when you have multiple of these things together, you want to use different numbers, different letters, which we'll see in a second, right? So in this case, B is equal to B1 E1 plus B2 E2 plus B3 E3. And so let's rewrite B again down here. Remember, B was X, Y, and Z. So B1 is the first component. It's just X. And what is our first unit vector? Well, it's just X hat. B2 is the second component. Well, that's just Y. And E2 is the second unit vector. Well, that's just Y hat. And similarly, this is just Z hat. Okay, cool. So now, let's combine all of this stuff together. I'm going to dot A with B. And we saw earlier, it's easy. I can just multiply those two column vectors together, and I'll just add the results. Now, we're going to write this in our new notation. So the first thing is we have AI, EI. Second one is, now remember what I said, we want to use a different letter. It doesn't matter what letter we use. Um, People like to use similar letters where it's easy to correct if I have a little miswriting, right? So in this case, I and J, if I accidentally write an I where I should have written a J, well, I can just quickly correct that. Or similarly, cross it out. That's why I think we like to use IJK a lot, um, or theta phi, because it's easy to like rewrite those things if you mess up. So here we have AI bj, because those are just the components. They're just numbers. We just multiply them together as usual. And then we're going to introduce this idea that we only want to multiply our unit vectors together, which we introduced above. But now we're going to introduce the Kronecker delta because, remember, the Kronecker delta had the property that it was 1 if I equaled j. And it's 0 if I doesn't equal to j. So we can now define this whole thing to just be delta I j. And so now the vector scalar product is and so what does this mean? It means we put this over here because my camera is blocking out. I can see. This means that we only need to consider what quantities? We only need to consider 1, 1 plus y. Viewer at home, why do you think that we need to do that? Hint, what is the definition of this new symbol that we saw? It's 0. Oops, sorry. It's 0. I forgot to cross this out. It's 0. It's 0 if I doesn't equal j. It's 0 if I doesn't equal j. So, technically, if we do this by the book, technically, we write this really as uh, 1, 1, AI, BI, plus delta 1, 2, A1, B2, plus delta 2, 1, A2, B1, plus delta 2, 2, A2, B2. That's really what we write out. But what do we know? We know this is 0. And we know this is 0. So we don't really care about writing out the 0 ones because it's just a waste of time, right? You can do it for fun. When I was younger and I didn't really understand this stuff that well, I would spend some time actually writing them out just so I convince myself that I could take that shortcut. I was not a very good, efficient individual when I was young when I came to this stuff. Especially when you see it for the first time, it's not so easy to kind of just do it. I'm telling y'all, don't waste time doing it. Don't waste time doing it. Once you understand the pattern that there's a lot of them going to be zeros, don't waste time writing it out. So, anyways, let's go back to let me just rate this real fast. So yeah, don't waste time writing out. I just did that there um, to show you in case you're at home like confused. Where did it go? Remember, it's because it's zero, right? Don't forget that. So now we can just replace everything we know. Well, delta 1 1 is 1. A1 is 1, and B1 is, oops, sorry, I forgot, we're working in 3 space right now. And then, of course, delta 3, 3, A3, B3. So sorry about that. I still thought I was working in 2 space for some reason. Um, but we're not working in 2 space, we're working in 3 space. So we have A3, 3, 3. So then this one is going to be X plus 1, 1, Y plus 1, 1, Z. And what do you know? We get X plus Y plus Z. Wait, isn't that what we got above? Let's go check. That is. So as you can see, these formulas work, right? So we just upped the abstraction, right? So instead of using, whatever I did off the top of my head up there, now you actually have a formula to fast track it. Can we do the same with the vector cross product? Well, the answer is, oops, let's see if this will drag up. Cool, 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 cool. The vector, the answer is yes, you can. So I'm going to introduce a new symbol. This one I believe is called the Levi-Civita symbol. And the Levi-Civita symbol says the following. Whoops. We have 0. So we have another time where this is equal to 0, right? But notice in this case we have 3 inputs. We have 3 inputs, not 2. We have 3 inputs. So in this case, it's 0, different than the delta case, where so if I equals j, it's 0. If I equals k, it's 0. And if j equals k, it's 0. So if any of the components are the same, so it's the opposite of the delta. If any of these, of the Kronecker delta, if any of these components are the same, we get 0. We have a condition where we get positive 1. And this condition is a permutation. It's cyclic. And what that means is you can always remember you get positive 1 because if I start with 1, 2, 3. Very easy, right? And it's the same idea as the last concept. It's the components are what the 1, 2, 3 are. They're referring to components. So 1, 2, 3, and then I just push it to the right. So I push everything to the right. The 3 wraps around, takes the 1 spot, the 1 takes the 2 spot, and the 2 takes the 3 spot. And then I do it again. I get 2, 3, 1. And then I have a situation where it gets a negative 1. And now you're thinking to yourself, oh, okay, well, that's good because when I had the cross product before, there were negatives there, right? And the negatives came from, the ideals of the determinant. But here, it seems like it's coming from the definition of a symbol. Maybe, maybe. That's where your mind should be going. If it's not going there, that's fine. Don't worry about it. In this case, we're actually going to start with 3, 2, 1. And once again, we're going to push everything to the right. 1, 3, 2. And 2, 1, 3. So this symbol, similar to the Kronecker delta we learned above, has conditions in which if I trigger them, I automatically put them in. So in this case, where if I'm never going to write out 113 because I had a repeated index down here, that's 0. So the only time I'm ever going to write these ones out are for 1, 2, 3, 3, 1, 2, 2, 3, 1, 3, 2, 1, 1, 3, 2, 2, 1, 3. That's the only time I'm ever going to write these out. And so now I'm going to write out the product, cross product for you. So remember, I need to get a vector here. So there needs to be a direction in this one. So I'm going to write out, I just defined the symbol, I should be using it. And we're going to do what we did last time. AI Vj, so the I and the j component of each vector. And now remember, the vector cross product needs to give me a vector. And so the last one is going to be the unit vectors. So in this case, we're going to be summing over the k's. In this case, we're going to be summing over the j's and summing over the i's. So let's write it out. And let me write over here, remember A was 1, 1, 1, and B was X, Y, and Z. Okay. Ooh, that's very close to the camera. That's very close to the camera there. Okay, so let's write it out. So remember, I only need to consider 1, 2, 3. And so I'm wherever I see that 1, I put it there. And remember, we're summing, so we're going to add them all together. And once again, I only need to consider what ones now? The ones in the negative 1. And you see, by the way, how this is a little bit easier than remembering the 3 by 3 determinant. If you just remember IJK, IJK, you're good to go. Components and a direction. It's a little bit easier than remembering the 3 by 3 determinant, in my opinion. And it makes it easier to figure out new formulas to write these things out. Because that will be in probably the next video, is how do you use all three of these to manipulate, triple products, for example. I think that'll be in the next video after this one. And so now we just simply plug in. I think here I will just write it for you. When we're talking about unit vectors, it's a basis, right? So remember, what is our basis here? What are our orthogonal um, coordinates? Well, remember, that's just x hat, y hat, z hat. So the first one is what? X hat. The second one is y hat. The third one is z hat. That's what these 3, 2, and 1 correspond to in this case. So if we write everything out, we get 1, 1, y, z hat plus 1, 1, x, y hat plus 1, 1, z, x hat. Now, the ones below we get plus, but now it's a negative 1. Remember, that's the definition of epsilon 3, 2, 1. It's negative 1. So we'll get negative 1, 1, y, x hat plus negative 1, 1, z, y hat plus negative 1, 1, x, z hat. Okay, now we can factor, right? Because we see that we have 2 y hats, 2 z hats, and 2 x hats. So if we factor, let's see what we get. So I'm going to focus on the x hats first. So it's this bad boy and this bad boy. If I factor out an x hat, I get z minus y x hat. And now let's do the y hat. So here's my y hat. So if I factor out a y hat, I get x minus z y hat. And then finally, if I do, uh, Let's see how yellow looks. If I do the z hats, I get plus y minus x z hat. And of course, in our column vector notation, like we did above, A cross B would give me z minus y, x minus z, and y minus x. Okay, is that what we got above? Does this formalism actually work? If I did it correctly, I should get the same answer I got above. Moment of truth. Z minus y, good. X minus z, even better. And y minus z. And so you see how naturally. Oh, did I mess up? Y minus x. Uh-oh. Y minus z. Oh, okay. Well, I just miswrote it. I was like, wait, I messed up. Y minus x. Oops. Sorry about that. So it's y minus x. I just miswrote it. And of course, the x minus z comes with the distribution of the negative. So we didn't mess up. We actually got it correct. And so you see how the middle component automatically took care of that negative sign. We didn't need to remember that it was negative sign here. This formalism took over it correctly. Let's have a little drink real fast. Okay. And so finally, let's get to the star of the show. What if I were to introduce you to a very interesting concept here, just to motivate you? This is not the actual definition. This is just the motivation of it. This is kind of just a motivational video. What if I were to introduce you to a concept that a unit vector is actually a differential? I'm not going to tell you why. I'm not going to motivate it outside of that. I'm just going to ask you to take that with a grain of salt, but I'm going to show you why it works. So let's say I introduce this new product to you. It's called a wedge product, and I'm only going to tell you this property of it. It's anti-symmetric. And what that means is if I wedge dy by dx, in your head, you want to think about this as unit vectors. This is the way I think about it. In my head, I'm thinking about this as x hat, wedge, y hat. Okay, so think about it that way. I'm multiplying unit vectors. If I wedge them together, what do I get? Well, nothing. This is just called a tomb form. But it's anti-symmetric. And what that means is I can rewrite this as dy wedge dx. That means if I switch the positions of these unit vectors, or in this case, these differential forms, that's what these are called. It's called differential forms. If I switch the spot of these differential forms, I get a negative sign. This is called an anti-symmetric product. It's similar to the cross product. The cross product actually has this property as well, that if I switch these places, I pick up a negative sign. And you can show this to yourself by calculating above. But for now, we don't need to. But that is a foreshadowing to what's going to occur, right? Because you're already saying, uh-oh, I have an anti-symmetry in the cross product. I have an anti-symmetry in my wedge product. However, similar to the cross product, something falls out. If you have an anti-symmetric product, what is a consequence of that? What do I write if I'm wedging the same thing? Think about that for a second. Well, if I follow the anti-symmetry, that must mean this is negative dx wedge dx. But what number is the same as its negative? Think about that for a second. What number is the same as its negative? Well, is 1 equal to -1. Actually, be a little fancy about this, put it above the equal mark. No! Of course it's not. Of course it's not. The only number this exists is for 0. Is 0 equal to -0? Well, of course, because the way you want to think about this is the negative is a multiplication of -1. So this really is equal to -1 times 0, and anything times 0 is just 0. So the only time this can be true is if this is equal to 0. So we're going to use this property to derive the cross product. And so I'm going to write out the formula for you real fast. A cross B is going to be equal to something clearly with them wedged together. And I'm going to introduce a new thing to you. It's going to be this thing called the Hodge star. And you'll see what that means in a second. But first and foremost, I want to rewrite A in my new notation. So remember above, we were rewriting it as AI, the components, times the unit vector in that direction. Well, we're going to start using this new differential form notation. I'm going to define this for you today to be AI dxi, where this is now the differential form component of your basis. So in our case, we have the orthogonal basis of x hat, y hat, z hat. Today, by definition, of course that's how it always goes. You have a pretty bracket on the left side, but the right hand side sucks. By definition, it's going to be dx, dy, and dz. So this is just by definition. Remember, this is just getting introduced. I'm just lecturing at this point. Right? I'm just checking if I can go from the vector cross product to the exterior product in one go. So we're going to do it. So by definition, this is what we're going to write out. And so I'm going to now focus on this A wedge B, right? So then, of course, B hat is then going to be PI dxi. And remember, those letters, it doesn't matter. As long as the ones that I'm summing over stay the same. It doesn't matter if I call them an apple, a smiley face, it don't matter as long as they stay the same. So let's use our new product. A wedge B is going to be AI dxi wedge. In this case, I'm going to pick something that's easy to rewrite if I mess up writing it. So I'm going to pick J dxj. And so above, when we were looking at our wedge products, we didn't care about the components. We only cared about the forms wedging with the forms. So we can now rewrite this as AI, because that's just a number, BJ, because that's just a number, times dxi wedge dxj. So what can this be written as? Well, remember what we saw above, that if I have the same thing, oops, sorry, that's not the same thing. If I have the same thing, it equals 0. And the reason for that was what? The anti-symmetric property of the wedge product. So in this notation down here, if dxi wedge dxi is equal to this, which is equal to 0. So the only ones I need to consider are when I and j are not equal to each other. Wait a second. Is this starting to sound similar to a symbol we defined up earlier? A little bit, right? So how many components are we going to have? 6. Why are we going to have 6 again? Uh-oh, is this sounding similar to a symbol above? We're only going to have 6 components. Why is that? Well, we can eliminate when both i's are 1. We can eliminate when both i's are 2, and we can eliminate when both i's are 3. So that takes away 3 possible components. So this now becomes A1, BJ, sorry, not BJ, B2, Y. We can't write 1 because if I were to write A1, B1, I would have to write dx1 wedge dx1. But dx1 wedge dx1 is what? It's 0. So I don't ever want to write that one. So we get A1, B2, dx1 wedge dx2 plus A1, B3, dx1 wedge dx3 plus A2, B1, because we could do that, dx2 wedge dx1 plus A3 B1, because I can write that, dx3 wedge dx1 plus A2 B3, sorry, let me write that a little bit better for you, dx2 wedge dx3 plus A3 B2 dx3 wedge dx2. And so that's all I have, right? Those are the only 6 components I can have, right? I have all the combinations of 1, 2, 1, 3, 2, 1. I have 1, 2, 3, 1, have that. 2, 3, 3, 2, right? So we're going to now, right? By the way, this is the physicist way of doing stuff. You notice how more abstract we're getting. I'm not even plugging in the numbers at this point, right? I'm just writing it out, and at the end, I'm going to plug in the numbers. So here, we're going to use the anti-symmetry product. Sorry, the symmetry property of the wedge product, right? Remember what we wrote above. dxi wedge dxj is equal to negative dxj wedge dxi. So, do you see situations in which we have that? Are there situations here in which I have these ones flipped around, where I have like a 1, 2, and then another one I have a 2, 1, where they're flipped around? Yeah, there's a few of them. Let's see if we can find them. So I'm going to hunt for the first one. I'm going to look in my differential forms for the components 1 and 2. So this is 1, 3, not good. Oh, I found it. Here's a 2 and a 1. So these two are going to be related somehow. So in this case, you want to keep 1 the same. So in this case, I'm going to keep the first one the same. I'm going to keep the A1, B2. I'm not going to flip this one around. But in the second one, I'm going to flip around these components. I'm going to flip them. I'm literally going to flip them. I'm going to use the anti-symmetric property of the wedge product, which means I can rewrite this as negative 1, 2. So this becomes a negative dx1 wedge dx2, which means this whole thing now becomes a negative. So this whole thing now becomes minus a2 b1 dx1 wedge dx2. And so now that's what I want, because I want to factor out whatever the heck this is. Whatever the heck this is, I can still factor it out. That's just algebra at the end of the day. So I'm going to write this as minus a2 b1 multiplied by dx1 wedge dx2. And so I'm going to repeat that for the next one in line. I'm going to repeat that for the 1, 3. So I'm going to look for the 1, 3. I have this one up. I found it over here. We have the 1, 3 over here. So once again, I have 3, sorry, I have 3, 1, right? Oops, sorry. For you guys, it's like this. I have 3, 1, right? I want to rewrite this as 1, 3. I want to rewrite this as 1, 3. So in this case, I'm going to use the antisymmetric product for this 3, 1. So I'm going to rewrite dx3 wedge dx1. This is equal. That means I can rewrite it as negative dx1 wedge dx3, which means dun, 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 this whole thing becomes negative. So now this is going to be plus a1 b3 minus a3 b1 dx1 wedge dx3. Okay, finally we have the last one, right? So we've done this one, we're done with it. And finally we have that last one, which is 2, 3, 3, 2. So let's write this last one in blue. Plus, and of course we're going to simply flip this one around. So we're just going to flip it around and write it as negative. So we're going to get a2 b3 minus a3 b2 dx2 wedge dx3. Okay, so before I introduce that hodge star, if I was doing this completely, I would just hodge from here. I don't really care. But for the viewer at home who may be the first time they're seeing this, if you're watching this 47 minutes in, I appreciate you. Um, Here is where we're going to start plugging stuff up. I wouldn't recommend it, but for the viewer at home, I kind of think this might be a little abstract. So we're going to start plugging in stuff. So remember, our vector was 1, 1, 1. Actually, let me write this over here. So remember, our vector was and so here we're going to start plugging in stuff. So where A1 is 1 times x minus 1 times, oh, sorry, B2 is y, my bad. Y minus x dx wedge dy. So you're starting to see that, uh-oh, this is kind of looking a little bit like the cross product above, right? Here I'm seeing that I have a y minus x. That's a good sign, right? If if you were doubting that this formula could ever reproduce the cross product, now you might be a little dubious of your doubt because uh-oh, that y minus x kind of looks familiar above, but it gets even better. If we plug in this one, the a is always going to be 1, so let's just focus on the b's. The b's is just going to be z minus x dx wedge dz. Uh-oh, uh-oh, that's kind of looking like something above. That's kind of looking like something above. And so finally, we get the last formula. Z minus y dy wedge dz. Okay, so we're almost there, right? This is looking pretty good because above, that's kind of what we have. Let's go see if we have it, right? So we have a z minus y. Do we have a z minus y down here? Check. We have an x, y minus x. We have a y minus x down here. Check. And then finally, we have a z minus x, and we do have a z minus x up here. They're the same, right? Z minus x is equal to x minus z, question mark, right? That's where we're at. Does it matter how I write it? We'll see. We'll see. We'll see if something pops up. So we're good. So let's go ahead and do this. The last thing we have to do, the last thing we have to do is earlier I told you, and you may have believed me, that I can rewrite x hat as this differential form, right? Y hat as this differential form, right? I told you that. I said, hey, that's what we can do. But now I have something like this. What can we do to get rid of that? Is there something out there that can return us to what I want? I know above I have an x hat and I want that to be just a dx. Is there something I can do? Well, don't forget, there's one last component of the puzzle. Remember what I wrote out above. I said that A cross B was equal to this Hodge star times A wedge B. And this Hodge star is this cool little thing that only acts on our differential forms. And it acts in such a way that it will return a one form. It will return a one form. And the way you want to calculate it is you want to think about the space you're working in. And by the way, I'll probably do a whole video on Hodge star. It's a very confusing thing. You want to think about which space you're working in. So in this case, I'm working in Euclidean 3 space or Cartesian space. And what is a volume of that? Well, the volume of that will just be simply the dimensions multiplied together. In this case, I'm going to do dx wedge dy wedge dz. Why can I call those the dimensions? Because think about it. What are the basis of your space? It's just x hat, y hat, z hat. So in this case, the dimensions in my informal way of looking at it is going to be dx wedge dy wedge dz. So the Hodge star is such the thing that I'm going to insert this at the start. So in this case, I remember, let me write this here. This is my end goal. I want to have this as my end goal. So when I'm Hodge starring something, I'm going to rewrite it like this. I'm going to put it at the start. And whatever it takes for me to get back to this form, that's going to be the answer. So in this case, right? So let's rewrite this below. So we're here. We are here. We're starring A wedge B. And above we saw that this was right like this. Y minus x dx dy plus z minus x dx dz plus zy. Hopefully I didn't get that backwards. Nope, okay. Okay. So, sorry, we have to, these new pages are interesting but fun. Oh no. Oh no. Okay, I have to do this so we don't cover it. Okay. So, now remember, our Hodge star only acts on our differential form. So, let's go through it. We're going to have y minus x star dx wedge dy plus z minus x wedge star dx wedge dz plus z minus y star dy wedge dz. Okay, so we need to figure out these three things. So let's do it. Using our formula above, or, the way I think about how to do this stuff. And of course, like I said, there's going to be an actual video on this next, but we're approaching an hour. And I will probably, this one will probably be like a few videos down because I want to do curl and um, divergence next. So let's now calculate star dx wedge dy. So remember, I'm going to replace this at the start and see how long it takes me to return back to this. Well, immediately we return back to it, right? We have a dz. So this is equal to dz. So this whole thing is dz. Now I need to figure out star dx wedge dz. Well, star dx wedge dz, we're going to write this as dx wedge dz. And what's left over is dy. So I'm going to now use my anti-symmetric property of the wedge product to move stuff around. So what do I want to do first? Well, I'm probably going to move this guy and this guy around, right? So if I do that, I get a negative out at the front, dx wedge dy wedge dz. So what is my answer? My answer is I have the negative of what I just did. The negative of dy, because dy was what the component was left over. So it's going to be negative dy, which, by the way, if you're thinking about it, is that the reason why there was a negative sign in the cross product at the start when you did it with the first time you're seeing it? This shows you why there's a negative sign, right? Simply by the anti-symmetric product. There is a negative sign in order to return back to this volume. And so finally, and by the way, you could have introduced the negative sign by writing it as dz wedge dx. If we did dz wedge dx, let me just show you that real fast. Let's say I'm at the start, dz wedge dx. Well, this would be dz wedge dx wedge dy, right? And so I get a negative sign by flipping these ones around. So this becomes negative dx wedge dz wedge dy. And so you see, I get another negative by flipping these around. Well, that's actually just dx wedge dy wedge dz. So you see, if I flipped them initially, I would have picked up a minus sign here, which gets counteracted at the end. So some people just rewrite it as dz wedge dx. I'm stubborn. I'm stubborn. Um, I don't ever remember to flip it naturally. Um, I'll just write it as negative dy over here because I know I need to multiply by negative to get my volume element back. Okay, so finally we're left with wedge dy wedge dz. So we're left with star dy wedge dz. And so if I do this, I'm going to write this as dy wedge dz wedge dx. Okay, so remember guys, I want to get back to my volume form. So I'm going to multiply, I'm going to flip these spots. So I get a negative dy wedge dx wedge dz. And then I'm going to flip these spots. And I get a dx wedge dy wedge dz. So you see how by the end, by the end, I don't have a negative sign. So that means this is just going to be dx. So finally, if I rewrite my stuff above, I get A cross B, which is equal to star of A wedge B, is now equal to dun, 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 y minus x dz plus z minus x times negative dy plus z minus y dx. So, just like I did way above, I'm going to distribute this negative through here. And so if I did this correct, A cross B is C minus Y, X minus Z, and Y minus X. Because remember, dz is just z hat. dy is just y hat. And dx is just x hat. And so, did we do it correctly? Let's go above and see. Z minus y should be the first one. Cool. X minus z should be the second one. Cool. And y minus x should be the third one. Cool. So I'm gonna end it there because this went on for an hour. Um, and so in the next video we will do a dot b in this new formalism, and it's a little bit different. It's going to be star a wedge b, right? So that means we're going to have to use a hodge star on a first and then multiply it by b. You know what? I'm so goddamn excited. I'm going to do it right now in front of you. I'll give you a little preview. We're going to do a star. So remember, what is a? A is this. So this is going to be star of a1 dx plus a2 dy plus a3 dz. And then the star is going to apply to all of these. So we're going to figure out what is dx, what is star dy, what is star dz. A little preview. Wow, what could that do, right? And then what if I star this? What does that even mean? Um, what about divergence? What about divergence? What about curl? Well, you guys know and love this one. This doesn't change anything. This is just x, y, z. You know, um, fx, fy. Actually, we'll save this for next time. We'll save this for next time. I'm getting a little tired. But I will tell you this: we can rewrite it in this formalism. What's this? We'll talk about that next time. What's this? Star F? Wow, we already know what the hot star is, though. We already know these things work. Um, but yeah, and so from here, this is where the cool stuff in physics can start to begin. But we're gonna call it there. Like I said, this was just I wanted to practice on my tablet. I just wanted to see where I'd go with this concept, and we went a lot of places. So hopefully you guys enjoy where this series will go because I'm not sure. Like I said, I think I want to. I personally, by the way, if you made it to the end of this video, cool. I personally kind of want to see where I can go with this form. I've never explored Cartan calculus in terms of, like quantum field theory or even like quantum mechanics. I know you can because if we start with, like a Hamiltonian ideal with our symplectic two forms, I know we can get there. But I have never done it personally, so I'll have to look into that. Um, so yeah, the next video, we're definitely going to go into this cross and dot product. So sorry, not this cross product. This curl and divergence. So see you next time.